Alright, let's do this. We got ourselves a new video of another question given to me by a student. So today let's learn about eels. Here we go. We're going to learn all about eels. Here they are. Beautiful little things, aren't they? Stunning little things. Stunning! I just made a pun. So, do electric eels actually make electricity? Yes, indeedy. Yes, indeed they do. So here's a cute little video, and what we're going to have here is an eel in a tank of water, and that is not a real hand. They're going to mention it there in the video, but the hand itself has actually been lined with a whole bunch of LED lights. So if it gets any electrical current going through it, the lights should light up. And as you can see from the video, as soon as it goes up that arm, zappity zap. Here we go again, slow motion. It's interesting, we didn't know this until recently, that eels like to jump out of the water at things and light them up, so to speak. So we're getting a huge amount of voltage going through this arm, a massive amount. It's a really big current. So the question is how is it creating that electricity? And actually, in the research I just had, it turns out there are some things I didn't know about electric eels, which I think are pretty cool, which is why I wanted to make the video for sure. Because there's just some things about this that I never knew about, and I thought were really neat, and I want to share them with you. So first off, how do these amazing little things actually create the electricity that they use to stun animals so they can eat them, or sometimes in defense? There's actual videos. I didn't want to show any on this one, but there are videos of electric eels killing alligators, whole alligators, basically killing them by running that electricity right through their heart and stopping that heart. So in order to answer this question, we have to look at something known as electrocytes, because electric eels actually have a really strange little thing in them where a large amount of their body is composed, well, actually their body is composed of three main organs. There's electrical organs. Now I'm going to get into why there's three of them later, but the main idea is that each of these organs have in them very tiny cells known as electrocytes. Now I'm gonna draw myself an electrocyte here. They generally kind of look like something like this. This is the general shape. Of course, I'm not doing an amazing job here, but this is generally what they look like. And what happens is that they are in fact actually filled up with negative charges. So let me see. I need to draw those. What I'm going to draw is, let me see. I'll draw a little. How am I going to do this? Tell you what. I'll draw a little circle here. I'll fill it up, and I'll give it a little negative sign. Let's see, negative. There we go. So there's my I guess my little electron, and let's just cut it out, bring it back, and I'm just going to fill this sucker up with a few of these so we can talk about this. So while I'm doing that, I'll just talk a little bit more. Now the interesting thing about the electrocytes is that they actually act in series. So what I'm going to do here is I'm actually going to show not just one, because this is kind of key to the whole thing, is that you can't just have one. Can't just have one. You gotta have more than one. So the electrocytes, these cells, are actually just filled all up with a bunch of negative charges, like you see here. Let me draw that one again. Close enough. But in fact, they're arranged in series. So let's draw this. Series, which means there's one after another. And what's neat is that everything I've taught you in both chemistry and in electricity is going to apply here. So this is actually a pretty useful topic. It's going to bring up a few things. Here, let me just bring in all of my happy little electrons. So it looks like this. Doobie-doobie-doo, doobie-doobie-doo. So We have all of these in line. Now, this is not entirely the whole picture. You see, there's a bunch of stuff in between. Let me draw them now. And I'm going to draw them. Let me see. I'm going to draw them showing them as like, whoops, whoa, that's not the color I want. I want this color. Much better. And let's just give ourselves black again. And I'm going to make a little plus sign. So, you might ask yourself, Mr. Gale, are you drawing protons? And I will happily say, no, I'm not. No, I'm actually not. And that's what's kind of interesting here. Protons do not flow freely, normally. In any case, electrons are. So when I'm drawing the electrons in the electrocytes there, those are electrons. But out here, we do not have protons, but we do have positive charges, which means where are they coming from? Where are these things coming from? Take a guess for a moment. Take a guess. In fact, what you're looking at there, and let me just pop up my little thing here. These, whoops, I want my brush. These are sodium ions. Yes, sodium ions. Holy cow, who would have thought that so quickly would we start talking about ions when it comes to biology? But there you go. So in its normal state, an electrocyte is basically hanging around with a bunch of sodium in it, surrounded and breaking it up. And as it stands right now, there's no movement of charges. If you think about the electrons inside, they're actually attracted to both sides, and they don't really move out very easily. So they're kind of captured inside the electrocyte. So what happens is that there's something else about these electrocytes that I haven't really drawn. Maybe I should draw it down. Is this? Yeah, right here. I'm going to draw a little, let me see. I'm going to draw a little something here. I think this will work. Maybe it won't. Maybe it will. But there's these little things. Now, it just so happens I'm going to call these by a special name. These are basically little openings in the cell membrane. So we're talking about something that's at a molecular level, very, very small. And they're basically what we call, let me write it down here just so that we have the name. These right here are called voltage gated, sodium channels. So this is the case actually. Whoops, that's a horrible S, but bear with me. This is interesting because most cells actually have these very, very specific openings in them that allow only certain types of ions or electrons or subatomic particles through. And this is actually how most cells regulate the in and out, how they sort of, I almost want to say breathe, but how they take in and take out certain molecules, ions, things that could help them out for energy or for waste disposal, any of these things. And so certain channels are dedicated to certain types of ions. And in this case, as you can tell, it's called a sodium channel. This thing only is able to let in and out sodium. So as a result, what happens? So as soon as the eel freaks out because it's, say, scared of something happening, it suddenly lets in sodium into the electrocyte. So boom, they all move like that. Now as a result, let me see if I can draw this real quick. All of the electrons are sort of basically charged only on one side. So if you had to think about this, let me just draw in red here. Draw in red, because red is a pretty color. Okay, so that means if I look at this, the electrocyte is now on one side very negatively charged, and on the other side positively charged. And then this one, positive, negative, and on and on and on. So what we have is a bunch of batteries in series. So what was once just simply a bunch of cells hanging out side by side are now suddenly, let me just draw this as an image here, is basically now a positive, negative, positive, negative, positive, negative. In fact, I probably could draw this even better. Let me draw this even better. It would be positive, negative, positive, negative, positive, negative. So if you think about that, remember when we used to draw how batteries are made up of cells? Hey, neat. They're called cells too. Cells. And then these are called cells. Isn't that cute? But the whole thing is one giant battery. So what happens is that each single cell has a certain amount of voltage difference. Remember what we talked about the last chapter about voltage differences. So each of them has approximately 0.15 volts. And then this is another 0.15 volts. And this is another 0.15 volts. So what's happening is that I'm getting, say this is voltage 1, and this is voltage 2, and voltage 3. And if I look at something like this, I got V1 plus V2 plus V3, and on and on and on. How many of these are there? Well, actually, as it turns out, there are thousands of these in a row, which means I'm basically multiplying this number right here by several thousand, and in the end, the EEL with one single burst is able to create up to 500 volts. One hell of a bang, and releases it. Now the way it works, let me see if I can just get rid of this, is that these are in series, as I said. So what's happening is that the electrocytes are starting, well, somewhere around here, and then they're in series all the way down. I'm not going to draw them all, but all the way down to the tail. So basically, this is one super long battery. And then, where's the wire? Remember, a circuit requires a loop. So how does it happen? Because what I'm getting here is I have suddenly a burst of electricity going through here, but of course it has to reconnect. We all know this because basically what am I looking at? I'm looking at this happening. But I need this, don't I? I need, let me see. I need my resistor. That is the, what would this be? Let's say it's a little fish that I want to kill. And then, so my resistor in this case for my circuit is something I want to eat and have the electricity run through. Here, I'll just make him look. I should have given him a little excise here. Hang on. I mean, if I'm going to do this video, I should do it right? All right, so there he is. There's little fishy, and now he's there. That's better. I don't think he'd have two eyes. Boom. Okay, I'm wasting your time. Here we go. So dead fish, wire. So what's the wire? Here's the fish. Here's the fish in the water. Give him a tongue. So what happens is that the wire is the water, which tells you something about what kind of water the eel must live in. Because if it's pure water, this is not going to work, which means electric eels must be in salt water to have a conductive material for its current to run through. And that's exactly what they do. They live in salt water. It has to be. Otherwise, if they were in pure water, they would never actually release any current whatsoever because they would have a closed loop. All very fascinating. But this leads us to something that's actually, in my mind, more interesting than the fact that they can kill animals by electrocuting the water. And this has something to do with the fact that earlier I said that they have 3 organs that produce electricity. And I want to talk about the one that actually, it does produce electricity through the water, but really low amounts, very, very low. It doesn't give these bursts of 500 volts. In fact, very, very small amounts. And that is known as the sax organ, because the sax organ is involved in what we call electroreception. Gee, Mr. Gill, what's that? Let me tell you. So electroreception is this fascinating thing, and I'm going to need to, let me see, I'm going to need to draw something here. Let's picture our eel. Here's our eel. He's very long. Give him an eye. So when, what we do know is that the eel is going to be producing a electric field around itself with the sax organ. So it produces sort of, it emanates this field. Now the field would almost, like, you might notice that this will look a little bit like as if it's a magnet. And it's sort of like that. Electric fields and magnetic fields have a lot of the same, I guess, ideas behind how we create them and everything, but they are different. Just so it's clear, magnetic fields and electric fields are different things entirely. So you don't want to mix them up. So we're here talking about an electric field. And what happens is that the electroreception is the fact that an electric eel can detect objects in the water. In other words, it's another way it uses to see things, find prey, find enemies, locate rocks, stuff like that. Because as you can see, this would be an electric field where nothing's in its way. But if I took an object, let me see, let me just change the color again. I'll draw something green. I haven't done green. Let's say that I introduced some object here that was a insulator. But over here, I'm going to introduce something that is like, say, a conductor. Now, most fish are, I'm pretty sure all of them, are conductors. You can run an electric field or current through them, just like we are. We're conductors. But a rock is sadly an insulator. So what happens to the electric field as a result? Well, that's what's kind of interesting. As a result, let's say here, the electric field can't go through the insulator. So it bends around. It bends around. Let me just get that color there. So what happens is that this happens. And so different parts of the eel's body now receive the other end of the electric field. And because of that, it's able to know that there must be something here. It's that sensitive that it can actually locate this object because of the changing field as a result. Same thing goes with the conductor. So if we looked at the conductor, I could say, all right, let's just, whoops, I just erased the eel's head. Okay, bear with me. Let's say, shoot. Draw back the head. There we go. Okay, so let's say we had a conductor. In that case, actually, the field would kind of, whoops, kind of gravitate towards it a little bit. And as a result, the location of the electric field where it touches on the body would actually get tighter, sort of less drawn out as it is on the insulating side. And as a result, also, it can locate that object on the other side. So this whole idea that we think that everything can see only with our eyes, there's so many other ways that our senses can work. And the eel is a fascinating example where it actually produces electricity and then can sense variations in its electric field that it produces around itself so that it can find things that way. And what's interesting about electric fields is that they can go through things. So if you think about it, an eel can look, say, behind a wall. It could find out what's behind a wall without actually having to look with its eyes, because if the electric field is going through, say, something that's not affecting the field, it would go through that object and then still get influenced by whatever's on the other side, and the eel would recognize that. So pretty tricky. Anyway, that's everything about eels. Thanks for listening, and I hope today we learned about eels. All right, later.
We hope you have enjoyed this video, and for more videos go to freakphysics.com.